Hi and welcome back to another new video of Basics of Electrical and Electronics Engineering, which is a subject for first year KTU syllabus students. So in today's video we are going to cover what is phasor diagram, how we can represent AC quantity using phasor diagram. In the previous class we have just covered what is meant by phase, what is phase difference, what is meant by lag, lead and in-phase concepts. Today we are going to study how we can represent the AC quantity using a phasor diagram. So these are the topics which we have covered in the previous class, and in today's class we are going to start with what is phasor diagram. So what is phasor diagram? Sinusoidal alternating voltage or current is represented using a line of definite length which is rotating in counterclockwise direction with an angular velocity of omega radians per second. Such a rotating line is known as a phasor. So what is a phasor? It is a line which is used for representing the AC quantity, and it has a peculiarity that it is always rotating in counterclockwise direction with an angular velocity of omega radians per second. So I'll show you how we can represent a phasor diagram. Just drawing a phasor, first a quantity, an AC quantity here. I have just taken a voltage quantity, that means voltage V is equal to, we will represent it by, because the angle is 0 or it is starting from the 0 point, we can say the equation for this one is Vm sine omega t. Okay, and this is omega t. Now we are going to draw the phasor diagram for this. So first what we have to do is, we have to mark the axis where we have to draw the phasor diagram. You can mark the axis like this. This is the 0 axis. This is known as the J axis. This one is known as the J square axis. And this one is known as J cube axis. Next we are going to draw the two peak values. I am just going to mark it on this axis. Here you can see this is Vm, and minus Vm also I am going to mark on this axis. Okay, so these are the 2 points. Keeping this as a diameter, we are going to draw a circle, and this becomes the trajectory of the phasor diagram, or we can say this is the circle or the way in which the phasor is going to rotate. Okay, so the phasor will be rotating in this circle. I hope you can imagine this. It will be rotating in this circle with an angular velocity of omega radians per second in counterclockwise direction, which means like this direction, with an angular velocity of omega radians per second. Next we are going to draw the phasor diagram. So what we are going to draw on the phasor diagram is the value the AC quantity is taking at this reference axis. So here you can see this is the reference axis, and at this particular point the value the alternating quantity is taking is 0, which is represented, I'm just showing it like this, which is represented here. Okay, here means its value is 0. I'll show you why, and we will represent it on the 0 axis like this. So this darkened line with an arrow mark here is known as the phasor diagram. We can remove all the axis, all the way in which the phasor is rotating, everything can be removed. We can just draw this particular line to represent in the phasor diagram. Before moving into a further concept of what is phasor diagram, let me ask you why we are going for this phasor diagram, or what is the need for studying the phasor diagram. For any mathematical calculations like subtraction, addition, multiplication and division of AC quantities like this, if you are having a voltage waveform and we are having another current waveform and you are asked to add these two, can we do it with the help of a AC sinusoidal voltage waveform? No, it is becoming difficult if we are having voltage and current as the sinusoidal quantity, and it becomes a complex process. So for this purpose, or for mathematical calculations or simplifications, we need some other way to represent this AC quantity, and this is done with the help of phasor diagram. I hope you understood why we are going for phasor diagram. So next we are going to study we are going deep into the concept of phasor diagram. So I have just marked the phasor diagram for a quantity which is starting from the 0 point. Okay, what value it is taking on the reference axis is to be marked here. Okay, now I'll just show you what happens then. You can see that this will be rotating in counterclockwise direction always. Just like the AC quantity is taking values from here to here. This value or this angle is pi and this angle is 2 pi. Let it be, this one will be pi by 2. You can see that after pi by 2 it will be having a value of maximum value is Vm. Okay. Similarly, at that point, where will the phasor being reached? You can see that after pi by 2 degrees of rotation, you can see that your phasor will be at this point. Or we cannot mark different points, but it will be rotating like this. I wanted to mention that. So now I am not going to represent this phasor here. Why? Because you will be flummoxed by different phasor diagrams. So this is the way you have to represent the phasor. Now one more idea I'll give you regarding phasor diagram. Where the phasor is marked as on the reference axis, for example in this one, what is the image it makes on the y-axis? This is the y-axis. What is the image the phasor makes on the y-axis becomes the instantaneous value for that AC quantity. Okay, once more I'll repeat. For example, if your phasor is at this point, in another example I'm saying, okay, so if your phasor is at this point or we have marked like this, then the image it makes on the y-axis, this much, will be its instantaneous value at that point, will be the instantaneous value at the reference point. You will get a good idea regarding this when we are studying what is lag, lead, and how we are marking all those phasor diagrams. So whatever be the phasor diagram, the phasor diagram makes an image on the y-axis. Image means it's just like a resolving. Okay, what image it makes on the y-axis, that much value becomes the instantaneous value of that AC quantity. I hope it is clear. So I'm just rubbing off all these things and we are going into the detailed concept of two waveforms which are in phase and how we can represent it using the phasor diagram. Okay, so first I'm going to draw two waveforms which are in phase, and for this purpose I'm just taking two waveforms like this. Okay, first one I'm just taking voltage itself, or we can just we can take it as a voltage, or voltage is equal to Vm sine omega t. Why? Because it is starting from the 0 point. Now we have already studied how to represent a quantity which is starting from the 0 point. At reference axis the value is 0, which means it is to be represented. I'm leaving all the axis. I'm just marking the phasor diagram on the 0 axis. Okay, because at the 0 axis when you are checking the image, you can see the value will be just a 0. Okay, that is why we are marking it on the 0 reference axis. I hope it is clear for everyone, and this one is known as the voltage phasor. So next we are moving to draw the current waveform which is in phase with the voltage waveform. Here you can see I have marked the current waveform I is equal to Im sin omega t. Now we are going to draw it in the phasor diagram. Just check what is the value it makes on the reference axis. What is the value it is making? It is again 0, which means you have to mark the phasor diagram on the same 0 axis of the phasor diagram. Or we can say this is the phasor diagram which shows two quantities which are in phase. Now can you identify why I have marked the value of current a little bit lower? Why? Because the magnitude of this one is also lower than the voltage. To show that in the phasor diagram I have marked like this. Okay, and you have to imagine one more thing. When two phasors are in phase or two quantities are in phase, both of them will be rotating together. As these points are being reached, okay, they are being together, always they are traveling together. So the same concept is there for the phasor also. You have to imagine that these two phasors are together rotating in counterclockwise direction with an angular velocity of omega radians per second. I hope it is clear for everyone. Next we are going to study how we can represent lagging quantity. So let's consider two waveforms. One is considered as as a reference, I am again marking voltage as the reference here. Okay, so V is equal to Vm sine omega t. Why? Because it has started from its 0 point. On the reference axis, the voltage waveform takes the 0 value. Again, on the phasor diagram, on the phasor diagram, again I am going to mark it on the which point? On the 0 reference axis. So your voltage phasor will look like this. Now, what about the current waveform? I am going to mark a current waveform. So here I have marked the voltage. I am going to draw the current again here. Okay, I forgot to mention the x-axis here. You can mark it as omega t. Okay, now let's continue with the current waveform. So how can we draw the current waveform? If it is lagging the voltage is taken as the reference here. I am going to mark it as lagging, for example, lagging current taken here, and it is lagging by an angle 5 degrees. So what I have to mark on the phasor diagram? Can anyone say how we can draw the phasor diagram? First I should understand what is the value it is taking on the what it is taking on the reference axis. So for that I am just drawing like this. So this is the value it is taking on the reference axis. If you can just imagine that this is the axis here, and the rotation trajectory if I am marking, only for this case I will be just drawing the trajectory. You can see this will be the rotation. Okay, voltage is a little bit higher than the current, so I have just taken the peak values of current here, and I'm going to draw the phasor here. So how should I draw? You can see here that the value of current is at this point, that this is the instantaneous value at this point, which becomes the y image of the phasor, So I'm taking this point, reference point. At reference, the value is this much. So this will be the image the phasor makes on the y-axis. So if this should be the image, then the phasor will be at this point. Okay, which means the current will be here. Okay, only for this case I am giving you a good explanation, but whenever you are drawing a lagging waveform, you can just mark it as current, which is lagging the voltage by an angle 5 degrees, Your voltage waveform can be drawn as the reference. You can draw the voltage waveform. Just draw the current waveform like this. Okay, only for the first time we are drawing the trajectory. I'll just show what is the concept. So next time onwards, we'll just draw the reference first on the 0 axis. Then if it is lagging, we will just draw a waveform, a phasor diagram, which is just under the reference axis. After 5 degrees of rotation only, it will be reaching its 0 point. The same thing can be understood from here. See, after 5 degrees only, the quantity will be taking its 0 point. 0 point means 0 axis. So here you can see after 5 degrees only, the current will be reaching the 0 axis. Is it clear? So next we are moving on to what is lead, or how we can represent two waveforms, one leading the other. Okay, so this is the voltage waveform. I have marked the voltage waveform, and this can be represented as V is equal to Vm sine omega t. Now, using the concept of the same thing which we have already studied, the voltage is to be marked like this. Okay. Why? Because it is starting from the 0 point. At the reference axis, you can see the value the voltage is taking is the 0 value. 0 image on the y-axis means it should be marked on the 0 axis. Okay, so next we are going to draw the current phasor. So before that, we are going to draw the current waveform. Leading waveform. So voltage is taken as the reference here. Current is leading the voltage by an angle 5 degrees. So here you can see this is the 5 degrees. Now we are going to mark this on the reference axis. Okay, For getting a brief idea, first I am marking the peak values towards this point. Okay, peak value is taken, peak value is taken. A little bit error in the figure. Okay, so this will be your axis. And this will be the trajectory in which the phasor is going to rotate. Okay, this should be at perfect center. Let it be. Now you can see that the phasor will be rotating in this way. So what is the value the quantity is taking on the reference axis? You can see this is the value, not maximum, but a little bit less than that. So I am again taking this one towards the y-axis of the phasor diagram, showing that this is the y image the phasor is making. Okay, so what should be the phasor? Can understand that it should be at this point. Then only it can make a y image like this. So this is the phasor to be represented, which is to be used for representing the current waveform. And the rotation angle you have to mark as phi. So simply if you are not drawing any axis, you will just mark like this. This is the voltage phasor, and somewhere here we can draw the current, not exact angle. So 5 degrees I'll mark here, which shows that the waveform has already completed the zero value 5 degrees before, and now it is somewhere at this point. Just have a look here. Zero axis is this one. This current was somewhat here 5 degrees before. Now it has rotated and reached at this point, at this particular point. I hope you understood this one. So I'll just briefly give you how we can write this one. Current lags voltage by 5 degrees, and here we will write as current leads voltage by 5 degrees. Okay, and one more thing, here you have to imagine that these two phasors are rotating together. Always there will be a phase difference between them. Okay, and they will be rotating together, not together, we can say they are rotating in same angular velocity. So always there will be a small phase difference, that is phi, between them. Same in the case of lead also, like the same. Now this has happened, why? Because we have taken voltage as the reference. If you are changing the reference quantity, then what will happen? Let's just go through. If current is taken as the reference, then voltage will be leading the current in this case, and vice versa in the other case. If current is taken as reference here, you can see that voltage is going back of the current, running back of the current by an angle 5 degrees. So we can say voltage lags the current by 5 degrees. I hope you understood. I'll just show you a small image which shows the phasor diagram, and correspondingly you can see the change in the alternating voltage or instantaneous value according to the phasor rotation. You can see here the red line which is rotating is the phasor diagram. Okay, whenever it is reaching this point, you can just check the value here, it will be 0. Okay, so just when it is reaching at this 0 axis of the phasor diagram, the instant value or instantaneous value at this point will be 0. Now according to its rotation by 90 degree, this instantaneous value will be the peak value, and going like this, the instantaneous values are actually marked with the help of phasor diagram. So I hope you got a good idea about what is this phasor diagram. Thank you everyone for listening. Stay tuned for the next video. Bye.